Hello all and welcome to this second video where we continue our journey in looking into the field of integration and anti-differentiation, part of calculus. Today we're going to look at a really basic look at anti-differentiation and then what is the definition of an indefinite integral. So in the previous video we had a brief look at what is a definite definite integral. So today is a little bit different. It's an indefinite integral. They're very, very close, but they are different. So let's start with thinking about if we start with some original function f of x is equal to x squared and we apply the process of differentiation to it, the process is differentiation and the outcome is we get a derivative. Now, what is that derivative? What is that outcome? Well, that tells us a gradient function. Tells us the gradient at any point. Okay. Now, what happens if we wanted to go in reverse? As I've sort of got this diagram here, is that maybe I'm told the derivative is 2x, and I want to do the reverse. I want to find out what is the original function that gave me the derivative 2x, or what functions have a gradient. Okay. We're thinking of here, this outcome is what functions have a gradient defined by f dash of x is equal to 2x. And as you can see here, I've written the word functions, okay, or slash with the s. Because, yes, f of x equals 2x squared has a derivative of 2x. But it all turns out that any function that is x squared plus any constant, and this plus c will become really, really important, any function that looks like x squared plus c, where c is some constant, will have a derivative that is 2x. So the process of going backwards here, and I've just done this via recognition because I've got, well, x squared, the derivative is 2x. Well, clearly then if I go backwards, the derivative is 2x, then the original function has to be x squared, but it could be plus any constant, because that could be a plus 2, and when we differentiate, the plus 2 disappears. What is this process called? Well, very imaginative name. It is called anti-differentiation. And this function that we get out is called the antiderivative, or also called an indefinite integral. We're getting an indefinite integral. But we'll just leave it as called an antiderivative at the moment. So that's what differentiation is in reverse. It's called anti-differentiation, and we get the original function, but we also have this plus c here. Now, let's talk a little bit more about why this plus c occurs with a couple of examples. And we've looked at, or hopefully you should have looked at last year, the version of the power rule that does anti-differentiation that enables you to get that original function. But let's have a quick look at some examples. If we started with f of x is equal to x squared minus 3x, we get the derivative of it and we get 2x. If we also take another function that is x squared plus 1 and take the derivative of it, we also get 2x. So an anti-differentiation is asking, when you do anti-differentiation, is tell me the original function that could have this derivative. So you're effectively given the derivative, okay? And I want to find out. I'm going to anti-diff, or just say for short for anti-differentiation. What are the original functions that have a derivative that's equal to 2x? Well, we've quite clearly have showed that, well, there's two of them. There's x squared minus 3 and there's x squared plus 1. But it turns out there's actually an infinite amount of functions that start with x squared and then can have any constant on the end. We could have x squared minus 99. Differentiate that, you get 2x. You could have x squared plus 24.293. you could differentiate that and you still get 2x. So whenever you anti-differentiate, you need to realize that, yes, we have this pattern of recognition that when we go backwards, well, 2x is going to go back to x squared, or we could have, if we know that x cubed, when we differentiate, it becomes 3x squared. So if we go backwards, well, it's going to go to x cubed, but it could be x cubed plus any constant. We don't know what we actually, I guess, what the original function was when we anti-differentiate. Okay. It could have just been x cubed, but it could have been x cubed plus 19. It could have been x cubed minus 33. So whenever we anti-differentiate, we have to put in what we know is going to be there, but also what could have been there as well with this plus c. It's one of really, really common mistakes that people forget the plus c, and then it runs them into issues. So to sum up, although the derivative is the same for both of these functions, this means there could be an infinite number of solutions, all with different y translation. This plus c, we can think of it as y translation. This is denoted by the letter c. Quick graphically, an example of this is that graph of x squared plus 3 is the same, has the same derivative as x squared plus 1, has the same derivative as x squared minus 1, has the same derivative x squared minus 99. All of those functions all have the same derivative. So when we anti-differentiate, we have to say that any of them are possible, which is why we need plus c. You always need this plus c when you anti-differentiate. Now, this is just looked at of sort of what I guess could be considered recognition of, oh, here's a function you start with, differentiate, and then go back. It's quite obvious what you're going to get when you go back. But what happens if you're just given the derivative? How can we go backwards? Well, there's a pattern that we can recognize when we differentiate, where we always have to multiply by the power and then take one from the power. And if we're going backwards, well, surely there should be something like that pattern in reverse, and there is. And this is the general formula for anti-differentiation for polynomials. So if we try to anti-differentiate, and that's what this integral sign is saying, is we want to anti-differentiate, okay, x to the n, so just a regular sort of polynomial. And when we anti-differentiate, just like when we were doing dy dx, when we were differentiating, when we anti-differentiate, we have to say what variable we're doing it with respect to. What's the variable that's normally being changed? And well, in this case, it's x is normally being changed, so we're anti-differentiating with respect to x. So you always need to stick this dx on the end. But where I was going with this is, if we start with something that's x to the power of n, it turns into x to the power of n plus 1, and then in front of it we put 1 divided by n plus 1. And this will work for any values of n that are rational, q means rational, except for -1. So what is rational? It's any number that can be written as a fraction of integers, but essentially it means any number that's not irrational. And irrational numbers we know are pi, e, square root of 2, or any, and this is any surd that can't be simplified. So square root of 3, those can't be simplified down. So this only works for rational. And at year 12 methods, we're almost always going to be dealing with rational numbers. To summarize this rule, though, it's quite easy to summarize, is all you're going to do is add 1 to the power and then divide by the new power. So if I want to integrate x squared with respect to x, that's what dx means, with respect to x, I'm going to add 1 to the power, so I'm now going to get x to the power 3, and then I'm going to divide by, so I can, that's what this is sort of showing. I could have also just put this as n plus 1 dividing by the new power, but we get that. Same with the integral of x to 4.5 is equal to, and we need to put the dx in. Oh, and I forgot the plus c. See, I've already started making that mistake myself. You must put the plus c. We're going to add 1 to the power, so we had x to the 4.5, so we're going to get 5.5, and we're just going to divide by that new power, and plus c. That's all that rule is saying. Add 1 to the power, divide by the new power. Yeah. So find the general antiderivative, and the antiderivative is what's defined as the indefinite integral. Before, very briefly in video 1, we talked about the definite integral is the area under a curve. The indefinite integral is just what are the possible functions that have this as the derivative. It's a sort of wordy definition. It's a little bit obscure, but I'll say it again. The indefinite integral is defined as the family of functions that would have this as their derivative. All is what are the functions that could have that as its derivative. That's what an indefinite integral is, and it's missing any numbers at the top and bottom of the integral sign. But as I was saying, let's do the process. So we want to find the antiderivative of 2x cubed. That means we want to integrate it, 2x cubed with respect to x, and so we're going to add 1 to the power, and we had the 2, and we're going to divide by the new power, which was the 4, so we get that, and plus the c, and we can simplify the 2 on 4 just to be x to the 4 on 2 plus c, and that's it. And just like the power rule, wherever we have terms separated by a plus or minus, we can just apply the power rule separately to each term. So 5x to the 4, so we're going to the integral of 5x to the 4 plus 3x to the negative 2 minus 1 with respect to x is equal to, add 1 to the power, so we get 5, and the original 5 was there, divide by 5 plus 3x. Now negative 2, we need to add 1 to negative 2, so that turns into actually minus 1 because it's negative 2 plus 1. And our new power is negative 1, so divide by negative 1. Now we get minus 1. Now, negative 1, that is sort of like saying negative 1x to the 0. When we have a constant and now we're anti-differentiating, we could think of that as x to the 0. So I'm actually now going to add an x in there. And that's just going to be to the power of 1 and divide by my new power. And then I put my plus c, and now I can just simplify. So I get x to the power of 5 minus 3x to the negative 1 minus x plus c, because we don't need to write x to the power of 1. And that's using the general formula. So it's a little bit, one thing is you can't get it confused with the differentiation rule, because we're flipping and flip-flopping between the two. You'll be flip-flopping between the two a lot. But yeah, this is add 1 to the power, and then divide by the new power, and then you need to just stick a plus c on the end. Whenever you have a constant, when you anti-differentiate it, you're going to end up adding an x in. Because if we think about, if we differentiate this now, dy dx is going to equal to multiply by the power, take 1 from the power, multiply by the power, so that becomes plus 3x, take 1 from the power. This negative x here is like negative x to the power 1, so I'm going to multiply by the power and then take 1 from the power, so I get x to the 0, which cancels, which gives me this constant. So whenever we have a constant, you need to add an x onto the end of it. Bit of evidence there for it. Rightio. The other thing, and this is sort of, I just taken as assumed in this, when we have coefficients out the front, they can be called coefficients. There also can be called the scaling factor. Okay, is that technically we can separate that out of the integral sign. So when we integrate 4x to the cubed, and it's all actually written here, we can technically take that out the front because it's just a scaling factor. It's just multiplied that x to the cube by 4. You could then anti-differentiate the x cubed, which, so we add 1 to the power, divide by the new power, so we get x cubed to the 4, divide by the 4, those 4's cancel, and we get the answer. So that's the mathematical reasoning for why this 2, because we didn't have anything here in front of the x to the end in this rule. Technically, we'd put an a there, and we could leave it out the front there as well. But it's not there, and it's not given on your formula sheet. But that's the mathematical reasoning for it not being too much of an issue, just like in differentiation. Rightio, so find y in terms of x if dy dx is equal to 2 on x cubed, and we have dy on dx is equal to 1/3 square root of x. So these are just like in differentiation. Where possible, you always want to try and change, when you're dealing with differentiation, anti-differentiation, where possible, you want to change them into like regular polynomial form. So I can change this into dy dx is equal to 2x to the negative 3. I can bring this up the top and make the power negative using my index laws. So we get that. So now we have this written in polynomial form. We can use our general rule because that applies to polynomials. So it follows on that y is equal to the indefinite integral of 2x to the negative 3, because we're reversing the process. That's what we want to find. We wanted to find y, and we were given dy dx. So we're going to do that, and we're going to do this with respect to x because it's asking for in terms of x. So y is going to be equal to, so with this we have our 2x, we're going to add 1 to the power, so that becomes negative 2, and we're going to divide by negative 2, and put our plus c on the end, and now we simplify, so we just get negative x to the negative 2 plus c, and if we wanted to, we could write this as negative 1 on x squared plus c, if you wanted to. Either of the second last line or the last line would be accepted unless the answer asks for it in a specific format, which this question hasn't. This next one, same thing. We want to get it in polynomial form, and any square root is the same as to the power of half. So we get that, and so y is going to equal the indefinite integral of 1, or the integral of 1/3 x to the half with respect to x. So y is equal to, we put our 1/3 in there, x, add 1 to the power, so we get 3 on 2, and we're going to divide by the new power and put a plus c on the end. Now y is equal to, now we have this 1/3 x to the 3 on 2 divided by 3 on 2. How do we divide a fraction? Well, we can multiply by the reciprocal instead, so we get 1/3 x to the 3 on 2 times by 2 on 3, so we're just flipping the fraction and multiplying by instead, plus c, and that simplifies down to the 1/3 times the 2/3 is going to give us 2/9 x to the 3 on 2 plus c. Right, how are we going for time? Oh, 19 minutes. One last example, and then I'll leave you this 2019 exam question to do for yourself. Well, let's go back to this example. Now, in all of these cases, we're just being asked to find the antiderivative. So what are the family, or what are any of the functions that could have that derivative? Sometimes you're given more information, and these should be, you could think of these as, I guess, initial conditions. Sometimes referred to as initial conditions, but it's just extra information. And in this case, we're told, not only are we given the derivative, but we're also told that f of 2 is equal to 0. And when we're given this extra information about the original, I guess the original or the antiderivative, because f is the antiderivative of f dash, so if we give an anti-info, this will allow us to find c, what the actual number c is, which one from this family is it, that one, that one, that one, that one, like from earlier, one of the earlier slides, which one of these, and it might turn out to make this work, it can only be this one here. out of those 5 options, or technically the infinite amount of options that plus c means. So let's have a quick go at this. So we have f dash of x, so f of x is going to be the antiderivative of 2x squared minus 3x with respect to x. So that is equal to, we have the 2x, add 1 to the power, so that becomes 3 divided by 3, minus 3x, add 1 to the power, so that becomes 2 divided by 2, put a plus c on the end. And we're told that f of 2 is equal to 0, therefore 0 must be equal to, and we substitute in 2, so we get 2 to the 3 on 3 minus 3, 2 squared on 2 plus c, so we're going to get 2 cubed is 8 times by 2 is 16 on 3 minus 2 squared is 4 times by 3 is 12 on 2 is 6 plus c. So we get 0 is equal to 16 on 3 minus 6. So we can change that to 6 as a fraction on 3. 6 3s are 18 plus c. Just going to come up over here. So now we get 0 is equal to negative 2 on 3 plus c. So c, or we could take the negative 2 on 3 across, is equal to c. Therefore, using that initial condition, that info about f of x, because this was saying that was f of x, we can say that f of x is only the function 2x cubed on 3 minus 3x squared on 2 plus 2/3. As we found, that's what c is. And that's it for this video. So to summarize, I'll go back to this very first slide. If we start with some original function and we differentiate it, we get the derivative, but now we're looking in reverse. When you're given the derivative and you're asked to anti-differentiate it, or find the original function, the original function could be any family of functions that has this plus c in it. And sometimes you are given enough information, like that very last example, to be able to find what that c is. That's it. If you have any questions, email, put on Google Classroom, ask in class, or put in the comments below. Thanks and have a good evening.